Bismillah ar-Rahman ar-Rahim. Good evening. Today we will talk about some important information about salt gel. To complete the last video, I talked about the advantage and disadvantage, and it was the most important one from these disadvantage was the cracks. We will talk on it, what these cracks, when and where is formed, how we can prevent it, how I could prevent it in my study. Salt gel kinds, the most famous salt gel kinds, which one I used, the synthesizes the perovskite, and talk about the most important perovskite was lanthanum manganite oxide, why we use it, why I selected the manganese as transition metal, what is the interesting things in this transition metal, salt gel to lanthanum manganite oxide, the parameters act on the salt gel, metal alkoxide, gelating process, and last thing will be influences in the chelation agent on the structure and microstructure, and some similarity, some comparison with my study. Let's start from synthesizes of perovskite. How much kinds of salt gel we have? We have alkoxide salts. This one I used it, and Pechenine methods. All of these three kinds are very famous in salt gel. Some different between them. For example, Pechenine methods. And Pechenine method is less sensitivity to moisture from alkoxide salt. I use alkoxide salt because it's easy to control, easy to produce, and cheap. Except precursors were not cheap. We can check its price from Merck company. Now let's keep going. Our most popular salt gel based techniques used in synthesis of perovskite, gelating agents are employed to prevent this important disadvantage in salt gel, to prevent the metal segregation, metal cracks in the final compound, which may occur as a result of various interactions between metal ions in the solution. These cracks will happen when the wet gel start to convert to be dry gel by using a simple evaporation process. I mean, increase the temperature a little bit more, the cracks will happen. How we can prevent it, we will discuss all of this information. When two gelating agents work together to complex all metal ions, gelating agent, a precursor solution is formed with all metal ions entirely bonded with each other. That means we can say gelating agent acts as a glue to be sure all the metal ions bonded strongly with each other. This method tends to reduce metal segregation after decomposition under heat treatment setting. This ratio should be high enough. Let me say, next video, inshallah, I will discuss how I used a long math function to calculate the agent ratio carefully, because increased or decreased, these agents will act on some different on the final product. The ratio should be high enough to ensure that all metal ions are tightly bound to their structures and prevents precipitates or cracks in the solution must be high enough. All of the, we must be sure to the precursor ratio, solvent ratio, and alkoxide salts That's mean the precursors. Different in one of these three important parameters will act on the final product. Now let's illustrate this shape. Is this shape, this picture illustrates to us the cubically crystal system to undoped perovskite oxide. Let me repeat that, to undoped perovskite oxide. That means the main function to it is AbO3. When A is one of the lanthanides, B in my work was transition metal and 3 atom of oxygen. We take this oxygen in my work from water. I explained all of that in the previous lecture. Let me explain another important information. Lanthanides A will be at the center of this cubic. At the same time, will be surrounded from B metal ion from all of these 8 corners to this cubic. By that, each B is surrounded with 6 oxygen. By that we will have octahedra shape surrounded the transition metal, the B cation. By that, can image A at the center, lanthanide at the center, will surrounded with 8 octahedra shape from all these 8 corners to this cubic. 1, 2, 3, 4, 5, 6, 7, 8. Now let's talk about this agent to prevent the cracks. In my study, they were citric acid and ethylene glycol. All of these are organic compounds compressed with the reverse with the solvents. They were inorganic liquid. They were water, pure water, and hydrochloric acid. The crystalline perovskite structure emerged in one state at 600 Celsius. It's very interesting temperature. The same thing I did in my work when I tried the gel to convert from wet gel to dry gel like foam and burn it, increase the temperature a little bit step by step to reach 600 to be sure the structure emerged, all the structure, perovskite structure emerged on this temperature. And level of crystallinity increased. It's important when the temperature increased. Why? Because at centering temperature, recrystallization will happen to the perovskite structure. Here, from this article, the author, the researcher, depend on this diagram. Let's did a simple comparison between this diagram and my study. I worked on reactant in solution, mixed and stirred. Here at first step, it was hydrolysis when I put the solvent and metal oxide precursor, mixed and stirred. Before that, I added the agent to after mixed and stirred to form sol formation. After that, wet gel to dry gel and heat treatment to achieve 600 Celsius. After that, calcination to can find the final produce of the perovskite oxide. Here, like we are saying, the annealing time is different. This research work on 8 hours, but I worked to 72 hours to after that leave it in the furnace, and take it when it reach the room temperature to give opportunity to myself to come catch it, to come deal with this, produce. Here, let's take a look by using this periodic table about the doped perovskite. I'm not dealing now with the ideal cubic perovskite oxide. Now I'm talking about doped perovskite. That's mean A1 minus X, BX manganese O3. Okay, manganese, A from lanthanides, it was lanthanol. B from alkaline earth material. I used calcium and tritium as a doped material. Manganese from the transition material I selected because it's very interesting and it has amazing advantage like the different Mollison state. We will talk all of that at next slide. Here, let's talk about ferroelectricity properties, strongly dependent on what? Why in my study I focused on the grain size and crystallinity, because all of these crystallinity and grain size depend on how I can say its important property related with the microstructure, I mean crystallinity and grain size with this ferroelectricity. What does mean? By decreasing the crystallinity and grain size, the ferroelectricity will decrease. My goal was to increase all of the crystallinity and grain size to can achieve good ferroelectricity properties. Now let's talk about the most important disadvantage of the sol gel, the cracks. Reasons where and when will happen. The transformation of wet gel here, when the magnetic fish, this small thing, it's converts, but it's hard to convert now on because this liquid is very pulsatile, how I can say, the intensity of this liquid is increased by that this magnetic fish is hard now on to convert in this liquid by increasing the temperature more to convert the wet gel to be dry gel. Here the cracks will happen by a simple evaporation leads to deformation of its primitive porous backbone. Some deformation will happen. This deformation is these cracks. The difference in the contraction speed from outside to inside is the main important reason to these cracks. The last reason to these cracks is the chemical reactions that lead the gelation are casing change. The gelation and the aging process. The gelation is change in the physical and chemical properties of the gel, and the aging reduce the shrinkage during drying. Reduce the shrinkage during drying. Because that, I use citric acid and anthracycline glycol to prevent the cracks and to can produce good products. Note if the pressure in the liquid were uniform, it's important I take it from this article. All of these three articles are the source slide. You can take a look to them. The lattice would be uniformly compressed and there would be no tendency to fracture. Actually, in my study, the pressure in the liquid were not uniform. I think this note talking about the ideal situation. Here, water is important G. I use it like a solvent, like interaction media, and the structure take the necessary oxygen, three atom of oxygen from water. Let me read this note. Water is a key parameter governing the salt to gel transition and gel time. It's important to this process, salt to gel transformation, transition, sorry, and gel time. And it has another advantage. I will say it in the next slide. Synthesis of lanthanum manganese nanoparticles. Here, let me talk about lanthanum manganese oxide, why it's very interesting, why I adopt this structure. Lanthanum manganese oxide is here, it's a cubic crystal system. It's undoped yet. It's perovskite with general formula, like I said before, which be atom occupies the vertex of perovskite lattice and six oxygen atoms surrounding it. Let me count it. 1, 2, 3, 4, 5 up, 6 down. That's mean every B cations. And the structure that's mean every manganese will surrounded with six oxygen. And lanthanum, let me say, at the center. That means the lanthanide at the center was surrounded with eight octahedral shape. 1, 2, 3, 4, 5, 6, 7, 8. A element, like I said before, occupies the center of eight octahedrons. The oxidation state, here it's supporting the oxidation state of B cation can be modulated by varying preparation steps during the perovskite structure, such as temperature, non-stoichiometry cation, and like I did, substituting lanthanum 3 plus by lower oxidation state cations such as calcium, strontium, barium 2 plus. Actually, I used all of these calcium, strontium 2 plus as element doping, or even higher oxidation statification such as Ce4 plus. All of that to work on B cation can be modulated. We can dealing with B cation with these simple points. One of these is substituting lanthanum by lower or higher oxidation. Here, from this article, salt gel technique is one of the easiest and most efficient methods to synthesize different lanthanum manganese oxide. Gel is clusters that bind to each other to form a single three-dimensional polymeric network. Like I said in the previous video, gel is three-dimensional polymeric network. It's reversed with gel. It was colloidal liquid. Here we have two kinds of catalyzed hydrolysis, acid and base. Actually, acid is weakly cross-linked gel. In my study, I worked on acid catalyzed hydrolysis because all of the solvent, all of the agents, ethylene glycol and hydrolysate and acetic acid were acid liquids. As not liquid, acetic acid was powder. Ethylene glycol was liquid, but all of these were organic and acid. Because that I was dealing with shape like that, let me say. Here, my structure diagram, when I put it all of the lanthanum manganate, exohydrate, manganese nitrate, tetrahydrate, citrinium, and calcium nitrate tetrahydrate as a precursors with solvent, water, pure water, and ethylene and hydrochloric acid. By that, I put it all of these two agents to prevent the cracks and be sure this all the structure will bond uh, successfully with each other to produce an aqueous solution loaded at 100 Celsius and increase the temperature a little bit to produce wet gel and convert it to be dry gel without cracks and started keep going to increase the temperature to reach 600 Celsius to be sure all the organic agents are disappear to produce nanoparticles at 600 Celsius. That's mean the final products, it were like a carbon pressuring. Before pressuring, it was a crushing process to can be sure I'm dealing with homogeneous powder. Pressure to be to produce tables. After that, furnace at analog temperature 900,100 Celsius to give opportunity to the structure to recrystallization again to can increase all of the crystallinity and grain size. By that, my goal to increase the ferroelectricity to this doped structure. Here's something missing here, the crushing process. Here, let's talk about the parameters that could be controlled in the salt gel method, including natural nature of solvent, pH of the solution, concentration and type of the precursor, organic, non-organic, which ratio we will put, which number, which concentration we will select to put in the liquid, in the glass. If this ratio increased or decreased, some different will be on the final product. Heat treatment, sure, of the material and aging time. In some articles, I noted when increase the temperature, annual temperature, too much with small aging time or not too much annual temperature with long aging time, that will make a huge change in the final product. And I think sometime can destroy the structure or make structure with not good properties. My goal was to 900,100 with 72 hours. That's mean the annealing time was not short. It was 2 3 days. Now let's talk about methyl alkoxide. Are most commonly used in salt gel as a precursors. Most alkoxides show excessive reactivity toward water. That's make it amazing. By that, when we put them together with a specific ratio, some interaction, some attack to oxygen will happen to can produce the metal hydroxide formation. This attack, this reactivity toward water lead to what? Lead to rapid hydrolysis. That's what we are want. Metal hydroxide formation, immediate precipitation. Repeat, hydrolysis, metal hydroxide formation, immediate precipitation. The reactivity of alkoxide can be reduced. Here, we will talk about if we increased or decreased one of these three important parameters: solvent, water, precursors. The reactivity of alkoxide can be reduced by modification with gelating agent. Gelation influences the gelation process, which is reflected in gel structure and properties of the final material. Here, let's talk about gelation and gelate. It's simple, important information. Gelation is the formation of bonds between two or more separate binding sites within the same what? Within the same linkage and single central atom. Single central atom. That means lanthanum will be lanthanide, or let me say lanthanide will be at the center to these separate structures. Thus, a gelate is a complex molecule containing heterocyclic ring, that means not homogeneous ring, formed by gelation. Complex molecule containing not homogeneous ring, formed by gelation. In order to achieve homogeneity and microstructure, that's my goal, of the final product, control over the sol gel transformation is necessary, and that involves control over the alkoxide hydrolysis rate and let me not forget the agent ratio. Now let's talk about the influence of gelation agent, why it's very important on the structure and microstructure of the final products. The amount of gelation agent suitable for addition to alkoxide depends on the ratio of the gelating agent and alkoxide, at which the coordination saturation of alkoxide molecules is achieved. After that is important, while partial replacement of partial replacement of alkoxide groups with gelation agent in the presence of moderate amount of water, sure, because water here it's a reaction